Today we're going to talk about parametric equations. And we've already talked a little bit about parametric equations during the semester as I thought it was appropriate. So what's a parametric equation? The answer is a parametric equation gives you points by x as a function of time and y as a function of time, t. Now, t could be another variable as well, but the point is I have a parameter, t, and each time I plug that in, I get a value x and y, and that traces out a curve. Okay, so the first example we're going to look at is how do you take a parametric curve and turn it into non-parametric curve. In other words, I start out with x as a function of t and y as a function of t, and then I want to get y as a function of x or vice versa. Well, the way I do that is eliminate the variable t, right? And I can eliminate the variable t lots of ways. One way is I can solve for it. Another way is I can solve for a particular expression involving t, which is what I choose to look at now. Okay, so our example is x equals e to the t, y is equal to e to the 2t, add 6. T element of the reals. Okay, I want to eliminate the variable t and get a relationship between x and y. Well, I notice, by the way, I don't necessarily want to solve for t here and stick it in there. That's too hard. And sometimes when I do that using inverse functions of functions that aren't naturally injective, like trig functions, I run into problems, right? But I notice here that instead of solving for t, I can actually write y in terms of e to the t. So here goes. Y is e to the 2t add 6. Well, e to the 2t is just e to the t squared add 6. And now what was x? E to the t, so that's x squared add 6. There you go. But the problem is, so I get y equal x squared plus 6. The problem is, though, y equal x squared plus 6 makes sense for any value of x, positive or negative. Now I have to go up here and look. X is e to the t, right? My parametric equation. Well, e to the t is a special function. It's strictly greater than 0. So while this function makes sense for any x, my parametric equation only makes sense for x greater than 0. So I need to put the restriction for x in here to be entirely correct. Okay, so y is equal to x squared plus 6. And it's only good for x greater than 0. Why? Because my parametric equation is only good for x greater than 0. All right, now let's look at the next example, example 2. This is a little more complicated. X is 2 sine t add 4, y is 3 cosine t subtract 2, t element of the reals. What do I want to do? I want to convert it again to non-parametric, which means I have to eliminate the variable t. Now, I don't want to solve for t in these equations because of what I talked about last time. Trig functions are not naturally injective. I have to limit their domain to make them be injective. So if I were to use inverse trig functions, I might lose some values. Better yet, I ask myself, do I know any relationship between sine and cosine? And the answer is yes, I do. In particular, sine squared t plus cosine squared t is 1. Right? One of the Pythagorean identities? Well, so if I solve for sine t here and for cosine t here, then I can plug them into this equation, and when I do, I have eliminated the variable t. All right, so solving for sine t here gives me sine t is x minus 4 add 2. Solving for cosine t here gives me cosine of t is y plus 2 divided by 3. And since I know sine squared plus cosine squared is 1, I can plug those things in, and lo and behold, I've eliminated the variable t. Now, in this case, up here, I had a problem, x equal e to the t is strictly greater than 0. But down here, sine and cosine, since t is just element of the reals, are going to take on all values possible. So there's my answer right there. All right. There are a couple of examples then of how you turn parametric equations into non-parametric. Now I'd like to talk about doing calculus on parametric equations, and we looked at those before. Calculus meaning, how do I find the slope of the tangent line if I have a set of parametric equations? And the answer is, well, the chain rule tells me that dy dx is simply dy dt divided by dx dt. So that's the way I can find dy dx, right? Calculus means taking derivatives and doing some integration. All right, let's look at example 3. Down here, suppose I want the slope of the tangent line, and here's my parametric curve. X is 2t, y is t squared add 3, and t is minus 1. All I do is take dy dx, write it as dy dt over dx dt, and now I take the derivative of y upstairs, that's should just be 2t. So let's make that correction. And the derivative of x is just 2. Let's make this correction here. And what do I get? I get minus 2 divided by 2, which is minus 1. All right, now let's look at another example. Find all horizontal tangents to this curve, t squared plus 3 and 2t, same curve as above. All right, so what are horizontal tangents? Well, a horizontal tangent is where what? dy dx equals 0. But dy dx is dy dt over dx dt. So how would dy dx be 0 if dy dt were 0 and dx dt were not? All right, so that's what I try to find. I take dy dt, I set it equal to 0. Dy dt, like we saw, was 2t. That's equal to 0 precisely when t is 0. And then I also have to verify that dx dt is not 0. Well, what is dx dt in this case? It is just 2. That's never 0. Therefore, I conclude that a point, the only point where I have a horizontal tangent is when t is equal to 0, right? So what's the point? Well, I have to take x and plug in 0 and y and plug in 0. Now, I don't plug it into dy dt or dx dt. I plug it into x and y up here, right? So x of 0 is just 2 times 0, and y of 0 is 0 squared add 3. So what's my point? 0, 3. All right. That has the slope of the tangent line. Next time, I think I'll talk about how one computes the arc lengths of parametric curves, and again, that's something that we've already looked at.